I think we can start.
Okay, so we finished this issue of monotonicity and strong monotonicity, and I showed you that the RFM is a strongly monotone system. And this is important for the theoretical results because many of the theoretical results actually hold for strongly monotone systems. And this is why we need this notion. Now, the next step is to talk about networks, but before that, I just want to say a few words about a paper discussing the RFM with stochastic rates. This will also be in the lecture notes that I've sent you or will send you. And this is really an implication or application of the spectral representation of the RFM steady state. And the idea is the following. Maybe we have a lot of mRNAs in the cell, and all these, I'm speaking about identical mRNAs now. So the same, many copies of the same mRNAs, but because the cell is so stochastic, and maybe these mRNAs are in different parts of the cell somehow, the rates that every mRNA experiences, so this is one rate, one set of rates, this is another set of rates, and so on. Every mRNA, although they are identical, somehow has different transition rates, because maybe here there are more tRNAs that the mRNA needs, and maybe this mRNA is located in some other place in the cell, and there the tRNA abundance is lower, maybe some initiation factors, maybe there's just noise. So there are many reasons to consider a case where even though we have several mRNAs which are identical, each one somehow experiences different transition rates. And this is what we want to do in this context of RFM with stochastic rates. So I need to introduce one. So now the lambda i's are stochastic or random variables. Now the lambda i's are random variables. They have some distribution. And once we draw from this distribution, we make a draw and we get this set of lambda i's. And then we draw again from this distribution and we get the new set of values, and so on and so forth. And the idea is that every time you get from this distribution a new set of rates, and you assume that these are the rates for this RFM, you wait until convergence to steady state. You assume the rates remain fixed until you converge to the steady state. The convergence to the steady state is, I remind you, exponential. And now you will have a distribution of steady states and also a distribution of steady state production rates corresponding to distribution of the lambda i's. And you want to say something about this distribution. What is the average, say, of the steady state production rate or something like that? You want to say something about the probability distribution of these based on your assumption that you know the probability distribution of the lambda i's. Now there is a small technical problem here. We always assume that the lambda i's are positive, so we cannot allow, for example, Gaussian random variables, because then they can be negative, of course. So we need to consider random variables that are supported over the positive numbers. So we say that a random variable x is supported. So I write this with capital X now to denote that this is a random variable, supported on R larger or equal to delta with delta larger than 0 if it can only take values larger than delta. because I want to make sure that when I draw these lambda i's, I never get lambda I which is 0 or negative. So I will only consider such random variables, and this actually causes some problems because we will use here the stochastic, the spectral representation. We know that we can get R from the Peron root of some matrix with the lambda i's, and in this matrix, usually when we speak about stochastic matrices, or in many cases, you allow here random variables, for example, Gaussian, but here we cannot allow this because the lambda i's must be positive, and also I have to compute lambda I to the power minus half. So of course, must be positive in order for me to be able to use this matrix. So just one definition that we need: a random variable x is called essentially bounded if there exists some scalar c such that the probability that x is smaller or equal to c is 1. So with probability 1, whenever we draw x, it will be it will take values between minus c and c. And then, when this happens, the L infinity norm of x, which we denote like this is now the L infinity norm of a random variable, is defined as the smallest c, so the infimum on c, such that the probability x smaller than 1, smaller than c, is equal to 1. This is capital X now, because all the time I want to emphasize that we are speaking about random variables. So I'm trying to look for the smallest c so that this indeed holds. This is the typical values that x takes are always between minus c and c. And now with this minimal notation, we can give a theorem which is based, as I said, on the spectral representation. I will just give the theorem without the proofs, maybe just a few words on the proof. I know it's Friday, and I guess people are tired. Suppose that lambda 0, lambda n in the RFM, in the n-dimensional RFM, are drawn independently from, are drawn independently according to the distribution of a random variable x supported on r larger or equal to delta, delta larger than 0. So again, I must assume that it takes positive values, this x, because the lambda i's must be positive. Then, what does the result say for the RFM? So this is just the assumption on where we take the lambda i's from, and we assume that they are drawn independently. There is one distribution of the random variable x, which is supported, always positive, so the values are always larger than delta. And then, what can we say? Then, as n goes to infinity, so we are looking for very, very large chains, of course, because we are doing averaging. And we use stochastic matrix theory. Stochastic matrix theory holds for very large matrices. Then as n goes to infinity, the maximal eigenvalue of the matrix A equal to 0, lambda 0 minus half, so on. You remember this matrix. This was the matrix on the spectral representation, and here it is symmetric. So this was the matrix from the spectral representation of the steady state production rate. So the maximal eigenvalue of this matrix converges as n goes to infinity to 2x minus half infinity norm of this random variable with probability 1, and Rn, this is with probability 1, and Rn, the steady state production rate, converges to this to the power of minus 2. This is just from the spectral representation. I know that I denote it now explicitly by Rn. Let me denote this also by An. Although this matrix is, you remember, in n plus 2, but I want to emphasize, sorry, now that everything depends on the dimension, because I take the dimension to infinity. And then as I take the dimension to infinity, all I have to tell you is this sigma n, the maximal eigenvalue, sigma n, to what does it converge? So sigma n converges to this. And once I know sigma n, I know Rn, because Rn is just this to the power of minus 2. This comes from the spectral representation. Spectral representation said that if you know sigma n, if you know sigma, R will be just sigma to the power of minus 2. Yes, you remember in the spectral representation, we had sigma from the matrix A, and then R was sigma to the power of minus 2. So once you know what the maximal eigenvalue converges to, you automatically know what R converges to. And this result is proven by looking at this matrix An and finding a lower bound and an upper bound for sigma n. And fortunately, it's not complicated. We can find an upper bound, we can find equal upper bounds and lower bounds. And using this equal upper bounds and lower bounds, we conclude that you converge to this. So let me, first of all, give an example, and then I will say perhaps something about what this means. So let's assume, this is example 17 in the pages I've sent you. Let's assume X is distributed according to this half normal distribution. What is this half normal distribution? It is something like the Gaussian distribution, but only over x larger or equal to some u. This is a distribution with two parameters, sigma and u. Sigma is actually a bad notation, but that's the standard notation for this distribution. And this distribution is given by something like this. So it's very much like the Gaussian distribution, but only the values are always lower bounded by u. We need this because, again, we need distributions for the lambda i's. Lambda i's are distributed like x. We need distributions that are positive. Otherwise, it doesn't make sense to take here a negative value and raise it to the power of minus half. It will be undefined. So we took, for example, in the simulation I'm going to show you, we took the case where u is 1 and sigma is 0.1. So your x is always bounded. It's always bounded, lower bounded by 1, and in particular it is positive. So this is like the Gaussian distribution, but only over values larger than u, and we took u larger than 1. In this case, the theorem here, I will just finish this and I will leave time for questions. Then theorem, what theorem was this? This was theorem 14. Then theorem 14 implies that Rn will converge to 1/4 with probability 1 when we take the chain very large length n. Let me show you here a graph which shows the results of some simulations. And I will do a share screen in a minute. I show you this nice graph. Just a minute. Just downloading the PDF. No. Just see this here. To put it here, then open the PDF. Okay, now I can do share screen. So as I said, all this will be in the lecture notes. You just see how I do share screen here. Share screen, PDF, allow. I hope that you can now see the PDF. And I'm showing you a graph here. Let me enlarge it a bit. Can you see the graph?
Yes, sir. It is visible.
Excellent, thank you. So what you see here are 3 histograms of 10,000 Rn values. First for chains, so we took chains of length 50 and we took 10,000 such chains, and each chain we draw the lambda i's independently from this distribution that I showed you, this Gaussian distribution, but only over positive numbers. And then we did the same thing. We drew 10,000 values, but now for chains of length 500, and later for chains of length 1,000. And then we just plotted a histogram of the steady-state production rate in all our chains. And what you see here, the theory predicts that R will converge to 1/4, so to 0.25. And what you see here, that slowly the histograms converge slowly, they converge very slowly, but if we take more and more histograms, they will become more peaked and slowly converge closer and closer to 1/4, which is the value that the theory predicts. Of course, it's not very far, even for 10,000, for a histogram of 10,000 RFMs, it's already something like 0.26 something, I don't know. So it's not very far from 0.25, but the convergence in general is a little slow. It doesn't converge very quickly. So this is what I wanted to say about the RFM with stochastic rates. The important aspect here is perhaps, okay, first of all, the classical theory of stochastic matrices doesn't work so well because typically we assume Gaussian variables, but here we cannot allow Gaussian variables because of because the lambda i's must be positive. So we need to do something a little different, and this is what we do. What is interesting perhaps is that the convergence of Rn does not depend on the specific distribution of X. So we took here, can you see the board now?
No. Board is not visual.
Can't see the board?
So your PDF screen is showing right now.
So just a minute. Now is it okay?
Yeah, it is.
Okay. And is it the entire board that you can see? It's okay?
Yes, sir.
Good. So what is interesting is that this is a universal result in the sense that I don't care so much on what is the exact distribution of X. I don't care
Can you
about
zoom
what
out
is
a little bit? Zoom
So
it out.
Alvin,
Can you zoom out a little bit?
zoom in or zoom out?
Zoom out.
Zoom out. Is this okay?
Yeah, this way.
Okay, thank you. So it doesn't care, we don't care too much about what is the exact distribution of this X. We just need to know that it is always positive. And then because it is always positive, this means that X to the power minus half is always smaller or equal to delta minus half. So this is well defined. This is well defined. And then we know that sigma n converges to this. And the exact details of the distribution, is it this distribution that is like Gaussian over positive, or is it some other distribution? This doesn't matter at all. All that matters is this value. So in some sense, perhaps this can say that how, in spite of a lot of stochasticity in the rates, still we get something ordered or we get something averaged, because as long as this distribution is supported over the positive axis, then we will have this limit regardless of the fine details of what exactly is the distribution. So I don't care what exactly is the distribution or what exactly is the noise, if you like. I only care about some parameters of this distribution, in particular this value, the L infinity norm of X to the power of minus half. So you can think of this basically just as another application of the RFM with another application of the spectral analysis of the RFM. Spectral analysis of the RFM gives us another application which is using the theory of stochastic matrices. So questions about this before I continue to networks of RFMs? Questions about this statistical analysis?
Michael, so this is basically an advantage of RFM to have a spectral representation in terms of continued fractions, but generalizations of RFM doesn't help us to get a continued fraction, so we don't get recursive equation so much. So how to deal with stochasticity in those models like RFMLK or some other model, generalized RFM models?
So far we only did this stochasticity analysis for a single RFM. I'm not sure how it can be extended to networks. I don't know what to say exactly. When I speak about networks now, maybe I will say a word about the spectral representation, because in these networks we have a lot of RFMs, and assuming that we prove that everything converges to an equilibrium, then for every RFM we have a spectral representation of the equilibrium. For each RFM separately,
Yes.
we know, using the spectral approach, some representation of its steady state. Now the question is, can we somehow combine together all these spectral representations to get something on the entire network? That's not trivial. Maybe it's possible, I'm not sure. But let me speak about RFM networks, and then you can ask again, and we can think about this together, okay?
Okay.
Okay. So networks of RFMs, and this will be either the last topic of our talk, of our course, or maybe if I have a little more time, I see, I don't know, it's hard to predict exactly how much time each lecture will take. If I have a little more time, I will also speak about the topic called game of entrainment, which I think is interesting and originated from analysis of the RFM, as I said. Okay, so up until now, we talked about single mRNA molecule and translation on this single mRNA. But in practice in the cell, in a mammalian cell, for example, it is estimated that we have this number of mRNA molecules and this number of ribosomes. So it's a huge factory for proteins. This is just one cell. And of course, all these mRNAs are connected in some sense. In what sense are they connected? So I have these mRNAs, and they all need ribosomes, and they all need tRNAs. So there is a competition somehow for the shared resources. And in particular, for example, another case you can think of, when a virus penetrates into say a human cell, what it does is actually it injects its RNA into the human cell, and then the human cell, the ribosomes of the human cell, they don't know that this is a viral RNA. They start producing it. And of course, then there are fewer ribosomes for producing the human proteins. So there is a competition. But even without a viral mRNA, there is a competition between the various mRNAs for shared resources. This is a very important problem because I told you that in biotechnology, often we try to manipulate and take over the biological machinery. We take carrot cells, for example, and we plug in mRNAs that correspond to human insulin in order to convince the carrot cells to produce insulin. But if the carrot cells invest too much effort in producing these insulin, in translating these mRNAs for insulin, they will not have enough resources for their own well-being, and then the cell may die, and then the factory is gone. So in some sense, we want to make sure that when we manipulate these cells, they still have enough resources to continue their existence, and that's important. So we want to understand, using networks of RFMs, all this idea of large-scale translation and competition for resources, for shared resources. So I will speak about the model from a paper about 10 years ago. And the idea behind this paper was the following. Let's take several RFM IOs, let's say M of these. We can take any number of, let's say, M RFM IO. So let me just remind you what was this. This was a model that looked like this. There was an input U. And this input controlled the initiation rate. So when UT is small, time t, and sometimes t, if UT is small, the initiation rate is small. And if UT is large, the initiation rate is increased. Think of this as something that multiplies lambda 0. So it just changes lambda 0 to a larger or a smaller value, depending on the value of the control. And all the rest were the standard equations of the RFM. And at the end, we also had an output. And the output was simply lambda n xn. So this is the protein, the rate at which the rate at which ribosomes leave the network, and also the protein production rate. So here we have U1, and here we have Y1, and here we have YM, and here we have UM. And the moment we have RFM IOs, we can connect them together, of course, because each one has an input and an output, and we can start doing connections. So how should we connect them? The idea is that there is also a pool here of free ribosomes, because we want to model competition for the free pool of ribosomes. And now this pool has an output, say G1Z, and it feeds all the initiation rates. So the initiation rates, the ribosomes for the mRNAs come from this pool of free ribosomes. And if we have more free ribosomes here, this G1 will be larger, and then U1 will be larger, and this would mean a higher initiation rate, because now we have more ribosomes in the pool, so of course they can feed the first RFMIO with more ribosomes, and the initiation rate increases. And similarly for all the other RFMIOs. And these G's are functions that increase with Z. So you can think in the simplest case, let's take Z divided by M, something like this, something that makes sense. It should be 0 when Z is 0, and it should represent somehow the fact that if there are more Z's in the pool, if Z is larger, there are more free ribosomes, then of course the initiation rate to all the RFMIOs will be increased. And what happens in the outputs? Well, the outputs feed back into the pool, because these are the ribosomes that finish translation, and as they finish translation, they disassociate from the mRNAs, and they become free ribosomes, so we add them to the pool. So now we can write the mathematical equations of this model. First of all, we have the models for the RFMIOs. So now X superindex 1 will represent the state vector in the first RFMIO. So all this will be, so the most difficult thing about this model really is the notation, because there are so many variables now, and you have to keep track of how to denote them so that you will know what is going on. So X with this one here is the state vector of the first RFMIO, and we have M of these. Each one can be with different parameters and also with different lengths. So I also denote the vector fields by F1 up to Fm, because they can be different. The vector fields can be different in the sense that I can have larger or shorter mRNAs, and also, of course, with different internal rates, because maybe these are M copies of the same mRNA, but maybe they are different mRNAs, and then each one has different lengths and different parameters. Now, each UI is just Gi of Z. It is fed, the inputs are fed from the pool, and eventually I need one equation for how the dynamics changes in the pool itself. So in the pool itself, what do I have? Oops, sorry. In the pool itself, I have like this. First of all the outputs from all the M RFMIOs, all the outputs go into the pool, so they add positive value to Z dot, and I have to subtract all the Zs that go and feed the initiation rate in the RFMIOs. So this is the expression, as I said, there are too many indexes here, but I will explain, but it's easy to understand what this means. Here I have this equation, so now U is G1Z, and also I denote this by X1, and also I denote this by 1, because these are the parameters of the first RFMIO. And then what I have here is all the inputs that come into the pool. This is what I have here. These all come with a positive. And all the outputs that drive, this is the rate of ribosomes that enter the first chain. So the first RFMIO. So I have to subtract it from the pool because they go from the pool to the RFMIO. And of course, I have to do this for all the RFMIOs because each and every one of them receives ribosomes from the pool. And now, how to analyze this? Well, it turns out that this is a strongly monotone system. So that's already a good start. Why is it a strongly monotone system? Let me try to explain. So what do we need to do now? This is the entire mathematical description of the system. And we need now to calculate the Jacobian and see that the Jacobian is Metzler and irreducible. So the idea is as follows. The RFMs, every RFM by itself is a strongly monotone system. We know this. And we just need to check what will be the effect of Z on the RFM. So I want to analyze what will be this quantity, because Z only appears here. In order to make sure that everything is monotone, I have to check all the entries in my Jacobian. Now, my new Jacobian will be very large. It will include all these state variables and also the Z. But when I come to calculate things, I don't really need to calculate everything because the RFMs themselves are monotone, strongly monotone. So let's just look on the effect of Z on the RFMs and on the effect of the RFMs on Z. That's all I need to do. So how does Z, where does Z appear in this RFMIO, in this equation? It only appears through U1, and it only appears here. And when I differentiate here with respect to Z, let's assume for simplicity that this is just Z divided by M, just for simplicity. And then you see that when I divide with respect to Z, I get something which is always non-negative. So this is good. This will be an entry, an off-diagonal entry in my Jacobian, where I take all the big network and I write a big Jacobian. This will be one entry in my Jacobian, and it is non-negative. And all the other effects of the Z on all the other RFMs will also be non-negative. So that's good. And also I have to check how Z is affected by the XJs. Because there is a minus here, a minus here, and a minus here, you see that sorry, this is like this. You see that dz dot to d xj1 is also non-negative because I have a minus here and a minus here. So when I differentiate, I get something which is positive, or at least non-negative. And this is all I need to show in order to guarantee that the system is monotone, and it's also possible to show that it is strongly monotone. Okay, so it is a strongly monotone dynamical system, and it has another very important property. And this property is what I call the first integral when we spoke about the RFM on a ring. So that was a good introduction to this topic, because here we also have a ring in some sense. All this is one closed system where we have some initial density of ribosomes in the pool and in the RFM IOs, we have some initial density. This density does not change. So the ribosomes cycle around from the pool to the RFM IOs and back, but the total density does not change. And what is the total density? The total density is, first of all, the density of RFMs in the pool, plus all the ribosomes in the pool, I'm sorry, the ribosomes in the pool, plus all the ribosomes in the different RFMIOs. So here, when I go from J1 to M, this is all the M RFMIOs. I sum up on all the M RFMIOs, and in every RFMIO, I sum on all the state variables. These are all the state variables of RFMIOJ, and it has some lengths NJ. The lengths can differ from one RFMIO to the other. So when I sum up all the ribosomes here, all the ribosomes here, and all the ribosomes here, I get something which is a constant. So this remains all the time equal to the value it had at time t, at time 0. This is for any t. So this is useful because now we have a strongly monotone system with the first integral, and there are known results on such systems, and the strongly is important here because the results are for strongly monotone systems with the first integral that says the following: take any, take all the initial conditions, so there can be many initial conditions with total density, say 3, just as an example. You have some value for the initial density, and you can distribute it in various ways. You can put 3 ribosomes here and 0 ribosomes here, or you can put 3 ribosomes here and no ribosomes elsewhere, or you can put 1 here, and 1 here, I don't know. You take all these initial conditions that correspond to some constant initial density, and the system, which is strongly monotone with the first integral, will converge to a steady state. So what does a steady state mean? It means that this will converge to some steady state value, and all the densities in all the RFMs will converge to some steady state value. In the steady state value, what happens is that there is a flow of ribosomes, but the flow, for example, into the pool and out of the pool is equal, so the density in the pool remains constant. And also, for each site here of the RFMIO, the flow in and the flow out, when we have this steady state, also the flow in and the flow out are equal, so the density in each site will remain constant. And this corresponds to the steady state value. So you distribute your 3 ribosomes as in any form you like, and if you wait long enough, the system will redistribute them in the pool and in the different RFMIOs in a way that corresponds to a steady state. And for any initial condition with a constant 3 here, there will be a unique steady state, and you will always converge to this unique steady state. So this is very much like in the ribosome flow model on a ring. And actually, the proof follows exactly from the same result. The strongly monotone system with the first integral has this property of convergence to a unique steady state. So this is useful because the next step, of course, we can say, okay, what happens now if we change something? What will be the new steady state? But first of all, we have to prove, of course, that there is a steady state, because maybe there are endless oscillations somehow, and then we just have to, there's no steady state, we cannot analyze the steady state. So from this theory, we know that everything will converge to a steady state, just like in the RFM or in the RFMR. And now we can ask questions about the steady state. So before we ask questions about the steady state, and in particular, how it is affected by competition, are there any questions about the model? I think it's called a ribosome flow model network with a pool. Ribosome flow model network with a pool. Questions about the model and what I said about existence of a unique equilibrium for every forgot now what it's called, a constant level set of age.
Sir, I have one question.
Yes, please.
Sir, does this U1, up to UM acts as some control parameters of the thing that controls the overall flow?
Can you please talk a little closer to the microphone? I can't hear you well in this room. Can you please speak a little slower and closer to the microphone? I'm sorry.
Sir, does this U1 into UM acts as control function?
I'm sorry, but I didn't understand. I'm sorry. Can you send it to me by the chat, or maybe Arvind, you have my WhatsApp?
Yeah,
Yes,
so can you hear me? So I'm audible enough?
Yes.
Okay, so sir, his question is basically, are this U1 to UM are some kind of control parameters or control functions that control the whole system?
The UIs?
Yeah.
Are you asking about the UIs? Yes, the UIs. Well, thank you for the question, first of all, and I'm sorry I didn't hear well. Now I hear better. Somehow Aditi's microphone is better than Arvind's microphone. Anyway, the UIs, yes. In the RFM, the UI is a control parameter, exactly, that's a good definition, that comes from the outside world and controls the initiation rate. It's natural to take the RFM and add a control that controls the initiation rate. Why? The initiation rate is the rate at which ribosomes enter the chain. So this is something that comes from the outside world, and it is natural to think that we have some control on this. Okay, so we can change somehow the density of the RFMIOs, or we can change maybe some initiation factors. Anyway, into the RFM, the first side comes something from the outside world, and it comes here. So it is natural to call this the control and add here this control parameter that controls the initiation rate. So this is an RFMIO is exactly an RFM plus added control from the outside world that controls the initiation rate. If at some point UT is 5, then the initiation, then just lambda 0 is multiplied by 5. And if at some point UT is 0.01, then lambda 0 is multiplied by 0.01. So we can actually control, in some sense, the lambda 0. Think of it as if we control the lambda 0. Now, in the context of a network, we assume that these correspond to the density of ribosomes in the vicinity of the RFMIO. And where do these ribosomes come from? They come from the pool. So if there are more ribosomes, so let's assume something like this. If there are more ribosomes in the pool, if the density in the pool is larger, then of course U1 will be larger. There are more ribosomes now, and because of this, the initiation rate increases. And if the occupancy of ribosomes in the pool decreases, then there are fewer ribosomes, fewer free ribosomes that can feed the RFM, and then U1 will decrease. And similarly, Y, this should be U1 because it's the first RFM, and this should be Y1 because it's the first RFM. Y1 is exactly the RFMs that complete, the ribosomes that complete the translation and leave the chain, so they are a very natural candidate for the output. And these ribosomes, in this model, once they leave the RFMIOs, they go back to the pool of free ribosomes because now they are free and can detach to any of the M RFM IOs. Does this answer the question? Is this okay?
Yes, sir. Okay from my side.
Thank you very much.
Thank you, sir.
Thank you.
So Michael, I have a question. So RFM is basically a model that is to understand translation in a cell. So it's of biological interest to biologists to use this model to inspect those variations in the rates and then deduct the production rate out of the cell. So are there biological papers that uses this model to actually inspect those cases in the cell and produce some, experimental investigations out of it?
Well, first of all, you are right, of course, that we are interested in the context of biology, and I will answer the context of biology. But in TASEP, using TASEP, some people modeled something they called the parking garage problem. And this is similar to what you have here. You have a parking garage where the vehicles come from, and you have TASEPs that represent, say, different roads, and the cars come from the parking garage and feed the different roads, and you want to understand what happens in the entire network. So of course you can do this using the RFM IOs as well. I think anything you can do with TASEP, you can also do with the RFM. So first of all, even though the model was originally designed to study translation and large-scale translation in the cell, it can have more applications. And in these other applications, maybe it's easier to somehow deduce. The problem in the cell is that we don't know, for example, what are the rates in each RFM IO. We don't know this function that tells us how the initiation rate exactly changes when there are more or less ribosomes here. So there are many, many open questions about the biology, because we just don't know this infinite number of parameters that we need here. So what we do is we try to get qualitative rather than quantitative results or applications or implications, and I will describe one such implication here that describes perhaps the effect of competition, rather than get exact qualitative results, because it's really very hard. The biologists cannot give us enough information, I think, to generate a real-world model of translation in the cell, I think. And I should say that this is actually good for us in some sense, because we can publish papers and we don't really have to show that this fits reality, because reality is still too complicated and we still don't know many of the parameters. And then the reviewers, if they say, show me a real example based on biology,
Yes, it's a
and we have
common
a good
question.
excuse.
Yeah.
We have a good excuse why we can't do that. Or we can sometimes invent some values here together with biologists and say, this is more or less realistic for some reasons. But in practice, because the problem of getting the right parameters in the cell is so difficult, it is hard to use such models for quantitative predictions. But for qualitative predictions, we can certainly get some results. And I will speak about one such result in the next, in my next talk, which is in, I think, 2 hours from now.
Yes, yes.
Sir, 1 hour.
1 hour, 1 hour from now. Okay. I can start now, but because we have just 5 minutes, I don't know if it's useful. I think it's better that we stop here. Of course, I will answer more questions. And then in the next talk, I will describe one qualitative application of this model. And then we will speak a little bit about the gain of entrainment, and then we can finish the course. So again, if there are any questions, please
Any question from the audience side? I think there are no further questions. So let's stop this lecture and see you at 4 o'clock.
Thank you. Thank you, Arvind, and thank you all for participating.
Thank you, sir.